Alright, today we're going to go through the general multiplication rule in tree diagrams. So below here we have our equation for the general application rule. General multiplication rule. So the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so remember that in doing this, it's A and B divided by the probability of A. So let's take a look at our first example. Do most teenagers have active profiles on social media? So we have a 2018 report. So 90% of teens ages 13 to 17 use social media. Of those, 83% have at least one active social media profile. So if we take a look at the breakdown for this, so the probability of social media and active profiles is going to be equal to the probability of having social media, which was the 0.9, times the probability of having an active profile and social media, which is the 0.83. So we multiply those and we get the 0.747. So let's take a look at the next example. Let's get a clean version. So Shannon hits snooze on the alarm. I'm sure most of us do that. So let's say the probability of her hitting snooze is 0.6. If she hits snooze, there's a 70% chance that she is late. So the probability that she is late, given she hits snooze, is 0.7. If she doesn't hit snooze and gets up, the probability that she is on time is 90%. So the probability that she's on time, so let's say O, given she doesn't hit snooze, remember the complement, is equal to 0.9. And I miswrote this. This should be that she is on time. So we're going to say O for on time. So there's a 30% chance she's late when she hits snooze. And there's a 10% chance that she's late if she doesn't. So that adds to 1. Okay, so let's look at our tree diagram. So let's say that if she hits snooze, and she doesn't hit snooze. So we know she hits snooze on 60% of the time, so 40% or 0.4. She doesn't. Okay, so if she hits snooze, let's look at being on time versus being late. So she's on time 70% of the time, which means she's late 30% of the time with 0.3. So notice that each of the branches will always add to 1. So if she doesn't hit snooze, she's on time or she's late. So she's on time 90% of the time, or 0.9. And she's late 10% of the time. So take a moment and make sure we are good with the tree diagram. Here's a cleaner version. Okay. So we use the tree diagram to show the sample space. So let's take a look at finding the probability of Shannon hitting snooze and being late for class. So we know, given our general multiplication rule, that the probability that she hits snooze and is late is equal to the probability that she hits snooze times the probability that she's late given she hits snooze. So if you look back at your tree, you're just following the branch for hitting snooze and late. So you're going to multiply the 0.6 times the 0.3 to get 0.18. Okay, so to find the probability that she is late, we have to include the probability of not hitting snooze. So let's take a look at how we came up with that value. So let's go to the tree that we made. So if we follow the branch for being late. So for snooze and late, we got the 0.6 for hitting snooze and the 0.3 for being late, and we get our 0.18. But we have to add not hitting snooze and being late, so when we add 0.18 and 0.04, we get to 0.22. So that is the probability that we are late. Alright, so you can pause the video if you need to go back and recap what we just did. Okay, so let's take a look at our next example about who likes pop music. So I'm going to give you a moment to read through. Alright, so we have users, 47% of which are aged 13 to 24, 25% are 25 to 34, and 28% are 35 or older. Okay, so as part of our tree diagram, we are there. Okay, 47, 25, and 28. Alright. So now, let's include 85% of our younger folks like pop. 25 to 34 fios have 59%, and 23% of the 35 and over users prefer pop. So that our tree diagram will look as such. So if we want to find the probability for users who prefer pop, again, follow the branch. So if we want the 0.47 times the 0.85, and then we're going to add the 0.25 times 0.59, and then we're going to add the 0.28 times 0.23 for that 23%. So we get all three of these values because all of these folks prefer pop, and then we take their sum and we get 0.6114. Okay, again, following the branches. Okay, so I'm going to pause for a moment and go to the next example. Alright, so some conditional probability questions involve going in reverse. So suppose that Shannon is late for class on a randomly chosen day, and we want the probability that she hit the snooze button that day. So now we're looking at the probability that she hit snooze given that she's late. So we'll look at the probability that she hit snooze and was late, and we already found that to be our 0.18. Again, following that branch, we found the probability of her being late in general to be 0.22. So if you do that division, you get the 0.18. Alright, so take a moment, see if you can do the last example on your own. Alright, so let's go through this example. So let's start with 1% of women aged 40 or over have breast cancer. So if we're dealing with that demographic, 1% or 0.01 have cancer, 0.99 do not. So that is this complement. So for women who have breast cancer, 97% test positive on the mammogram if 0.03 test negative, if that's their probability. So for women who don't have breast cancer, the probability of a positive mammogram is 0.6. So that would means a negative would be 0.94. Again, the branches will always add to 1. Okay. So if we're following our branches, the probability of cancer and a positive mammogram is going to be 0.01 times 0.97, which is 0.0097, right? Okay, so the probability of not having cancer and a positive mammogram is 0.99 times 0.06, which is 0.0594. Okay. So just the probability of having a positive mammogram in general would be the sum of these two things. So if we add 0.0097, we're going to get 0.0691. Okay. So let's explain how we want to find a probability if we select a woman age 40 from this population, they test positive for breast cancer in a mammogram. Let's take a look at what we got here, given those things. So we got these two values. So if we want the probability of cancer and positive, we found the 0.997. So if we have a given that they're positive, and we want the probability that they have cancer and positive, again, we do the division, and we get our 0.14, which is the 14%. I hope that makes sense. So remember, if you're looking at it from a perspective of a two-way table, the given is the positive mammogram, so we're only looking at this row. If 97% have breast cancer, if you do 97 divided by 691, ooh, let's use the pen. You're still going to get the 0.14. Okay, so complete the lesson app. Check the notes in Schoology for corrections, and I will chat with you later. If you need to, rewatch the video. Take care.